In this video, we're going to look at implicit differentiation. So far, everything we've differentiated has been of the form y equals f of x. Y was explicitly solved for, and then you had a formula, okay, or a function rule with x's in it, or whatever variables you're using. Sometimes, though, it's kind of difficult to solve for y. So we're going to look at a simple example. This one is easier to solve for y than others, okay? X squared plus y squared equals 1. It's the unit circle. It's a circle, right, with a radius of 1. It's not a function, right? When you solve for y, we move that x squared to the other side. We get y squared equals 1 minus x squared. Then we have to take the square root of both sides, and any time that we take the square root of a variable squared, we have to put this plus or minus over on the other side because it could be positive or negative. Either way, when you square it, right, it becomes positive. So there's actually two parts, okay, because this is not a function. This circle is not a function. So the y equals the positive square root of 1 minus x squared refers to the upper half of the circle, and y equals the negative root 1 minus x squared refers to the lower half. Okay, so this actually represents two distinct functions. So if we want to find the slope of the tangent line to the graph of the unit circle at the point 3/5, 4/5, well, we first have to figure out which function that's on. Okay, I'm going to estimate and sketch it in here. 3/5 is maybe right about there, maybe 4/5, yeah, right about in there. Okay, so we want to find the slope of that tangent line. So first we had to solve for y. Okay, so we're on the upper half of the circle there. So y equals the positive square root of 1 minus x squared. To make it easier to differentiate, I'm going to go ahead and write that as 1 minus x squared all to the 1/2. That way, when we use the chain rule, we bring the 1/2 down out front, leaving the inside function there, reduce the power by 1, 1/2 minus 1 is negative 1/2, and multiply times the derivative of this inside function. Derivative of 1 is 0, the derivative of negative x squared is negative 2x. Simplifying, those 2's cancel, the 2 and the 1/2. And I'll put the negative x up in the numerator and write this power of negative half down in the denominator as a radical. Okay, because I'm going to go now and plug in 3/5, okay, and see what the slope of the tangent line is at 3/5. So it'll take a little bit of work. So plugging in 3/5 for x, we have negative 3/5 in the numerator, divided by the square root of 1 minus 3/5 all squared. So simplifying inside that radical, 3/5 squared is 9/25. So the square root of 1 minus 9/25. So to simplify that, we need a common denominator. 25/25 minus 9/25 is going to be 16/25, which we can simplify that. Square root of 16 is 4, square root of 25 is 5. Now we can multiply by the reciprocal of the denominator, so the numerator is negative 3/5, times the 5/4 is the reciprocal of the denominator. My 5's cancel, so we get negative 3/4, which looks about accurate, right, that the slope of that tangent line is close to negative 1, okay? But there's a better way to do this, okay? Sometimes the functions are just really complex, like this one, okay? There's no way we're going to solve that for y. So instead, to find the slopes of the tangent lines on that graph, even though it's not a function, we can still find the slope of the tangent line, we have to use a new technique called implicit differentiation. So remember, you can do anything to an equation as long as you do the same thing to both sides. So why not differentiate both sides? Okay, and the key is to remember that y is a function of x. But before we actually take an equation and differentiate both sides, let's just practice differentiating expressions involving y, because it's a little bit different. So we're going to treat y as a function of x. So if we want to find the derivative of, for example, y cubed, this is really a function cubed because y is a function of x. So what we're really doing here is using the chain rule. So we're going to bring the 3 down out front times the inside function y of x all to the power of 2, right? The y is a function, so we keep it inside. And then we multiply times the derivative of that inside function, which is dy dx. People usually would just write this 3y squared times dy dx. Or you could put y prime. I tend to use the dy dx notation when I differentiate implicitly, though, because it's easy for that prime to look like a 1, and it's just easier to spot the dy dx. It's more clear. Okay, or say if we wanted to differentiate the product of x times y. We would still need to use the product rule because we're multiplying here. So it would be the first factor x times the derivative of y is dy dx plus the function y times the derivative of x is just 1. Okay, so it's x times dy dx plus y. Or to differentiate, say, 1 over y, first we would want to write that as y to the minus 1. And again, then it's just like this one. We're using the chain rule. So we bring the minus 1 down up front, times the inside function y, decrease the power by 1 to negative 2, and multiply times dy dx. And I'm going to drop the y there, or the 1. And I would write it like that. Okay, so how to differentiate implicitly? Here's some guidelines. We want to take the derivative of both sides, treating y as a function of x, just like we did in the previous few examples. If you're given some values for x and y, you can go ahead and plug them in. And then we want to solve for dy dx. And these last two steps are reversible. They can go in either order. So let's differentiate the unit circle implicitly. So we want to take the derivative of both sides. So I'm going to write derivative of the left side equals the derivative of the right side. Take the derivative of the entire sides. Now, the derivative of x squared is still just 2x. X is x. But y is a function, so the derivative of y squared is 2y to the first times dy dx by the chain rule. And the derivative of 1 is 0. And now we can solve for dy dx. So subtracting 2x over to the right gives us 2y times dy dx equals negative 2x. Dividing both sides by 2 makes those go away. And we're solving for dy dx here, the derivative. So we need to divide both sides by y, so we get negative x over y as the derivative. It doesn't look quite the same as the derivative that we previously got right here. But in fact it is, because y is defined as root 1 minus x squared. All right, up here. Y equals root 1 minus x squared. So this is the same as negative x over y. Let's see if we get the same answer, negative 3/4 when we plug in the point. Now, interestingly, now we have a y in our answer, so we actually can just use the corresponding y value 4/5. So to find the derivative at that point, so the dy dx at the point, 3/5, 4/5. It's negative x, it's negative 3/5, divided by y, which is right here, 4/5. Multiplied by the reciprocal of the denominator with negative 3/5 times 5/4, and we do get the same answer. Now, implicit differentiation is related to related rates. Okay, sometimes when you have two or more variables which are related, both of those variables sometimes change with respect to time. In applied problems, that's quite often. So supposing y and x are both related to a third variable t, dy dx represents the rate of change of y with respect to, shorthand there, with respect to t, with respect to t. And dx dt expresses the rate of change of x with respect to t. Okay, so if you want to find the rate of change of, I don't know, y with respect to t, perhaps, what you do is you differentiate implicitly, except instead of putting derivative with respect to x on both sides, you differentiate with respect to t, meaning you have d dt at both sides. Then, just as with implicit differentiation, you plug in your known values and you solve for whichever rate that it is you're trying to find.